Today, on Zenodilodon, this laser is an OPSL, a type of solid-state laser. It produces 488 nanometer laser light and is rated for 20 milliwatts. The laser driver is not made by the original equipment manufacturer, and its construction is a path of learning from the ground up. There are 0 digital components, and it's completely analog. In this video, you'll learn exactly how these incredible lasers work in detail. I hope you enjoy the information and story of how I conquered a laser that by its nature is constantly on a balance of operational parameters. The Coherent Sapphire 488-20. On the inside of the laser head, there is a ceramic optical deck that is mounted on top of a thermoelectric cooler. The optical deck contains many parts, both optical and electrical, and I'll discuss each one in detail. First in the laser's optical train is the pump laser diode, which produces 808 nanometer laser light. This laser light then travels through a FAC and grid lens. Here is an equivalent C-mount package laser diode, and it has a FAC lens. This stands for fast axis correction. Behind the FAC lens is the laser die itself. The bond wires go to the negative tab while the package is positive. To drive the pump laser diode, I reverse engineered a simple linear laser driver. And these laser drivers are about as simple as it gets with very few parts. The driver uses 4 main parts: an LM358 operational amplifier, a TL431 precision current shunt regulator, a low resistance resistor, and a NPN transistor. The TL431 creates a stable voltage with a resistor in series when connected to power. This stable voltage is used by the potentiometer and allows for a selectable stable voltage reference that goes to the LM358. In this circuit, the resistor of low resistance, which is typically under an ohm, is in series with the load, and it generates a voltage differential when current flows through it. The LM358 receives that small voltage across the shunt resistor and compares it against the voltage from the TL431's linked potentiometer. The higher the voltage is set on the potentiometer from the TL431, the higher the circuit will allow the voltage to be across the shunt. This is how current is controlled in a circuit. With this basic circuit working, let's discuss some modifications. I made a couple of different prototypes based on the simple laser pointer driver so that it could test some modifications. This one has a current set potentiometer as well as an additional jumper. Many laser drivers support modulation, typically a 0 to 5 volt range, which will allow for brightness control. This is one important feature I wanted to try to integrate into my circuit. Removing the jumper disconnects the output of the LM358 from the base of the transistor and turns off the driver, which is a crude step towards modulation. Higher current output is another thing I wanted to achieve with my drivers. Here is another prototype I made to test that possibility. This driver has been split into 2 sections, one section containing the LM358 comparing circuit, while the other has a small 3 transistor pass bank. The 3 transistors, each having a maximum current of 3 amps, are in parallel, and each transistor's emitter has a very low resistance resistor for throughput current balancing. In addition to that, another low value resistor is placed on each base to balance the input signal current. The collectors of the transistors are all connected, which lead out to the negative connection of the load. This driver can do 6 amps comfortably. Controlling the TEC, which stands for thermoelectric cooler, inside of the laser is highly critical. This TEC is on top of a heatsink and has a smaller heatsink with a thermistor attached to it. To control the TEC, I made a comparator circuit with a 555 timer for pulse width modulation control, abbreviated as PWM. This is an early prototype and has 2 potentiometers, one for temperature adjustment and the other one for power duty cycle. Setting the TEC temperature requires a little bit of patience, as reaching thermal equilibrium can take some time. I have chosen not to speed the video up to reflect that reality accurately. The temperature of the TEC is important because it prevents the laser diode from overheating. The secondary function is to control the exact wavelength of light it produces, as this will also change with temperature slightly. There are three LEDs on this TEC driver. LEDs are light-emitting diodes, but you probably know that already. The white LED indicates when power is going to the TEC. Below that, there is a green LED, and that LED is connected to the output of the comparator. Both of these LEDs will turn off when the temperature set point has been reached. The TEC driver will continue to cycle on and off as needed to keep the temperature stable. I'll discuss more on how the circuit works electrically later on in the video. For now, let's pay attention to its behavior. Adjustment of the temperature is relatively easy to understand. If I turn the potentiometer to set the temperature warmer, the white LED turns off instantly and will only turn back on when the temperature set point has been exceeded and the TEC turns on. When the potentiometer is turned to set the temperature cooler, the LED will stay on longer until the temperature is reached and the TEC shuts off. To the left of the white LED, there is a red LED. This indicates the PWM output of the 555 timer and behaves as an interrupter to the power signal. There is an inverse correlation between the red LED and the white LED. The red LED indicates the level of PWM interruption, pulling low the control signal going to the MOSFET that switches power to the TEC. Controlling the average power going to a TEC can drastically reduce the level of thermal oscillations caused by the delay of thermal mass heating and cooling. More on thermal oscillations will be discussed later in the video. When the 555 timer is set to a low PWM duty cycle, the white LED shines brightly while the red remains dim. This shows a low level of interruption with a higher average power going to the TEC. Increasing the level of PWM interruption is indicated by the red LED becoming brighter. This lowers the average duty cycle of the MOSFET and decreases the average current consumption of the TEC. However, adjusting this potentiometer will have little effect on the amount of time my finger covers the power supply's voltage and current indicators. When the 555 timer's PWM is higher, the red LED is brighter. This indicates a higher percentage of interruption to the MOSFET. Since the white LED is tied to the power going out to the TEC, this will be dimmer. After making several prototype circuits, I set out to make a complete driver. I know the Coherent Sapphires are single TEC lasers. This laser driver has a constant current output for the pump laser diode, another constant current output for the TEC in the laser head, and if needed, another basic temperature controlled output for additional fans or TECs. Before connecting the driver to the laser, it's wise to do testing on dummy loads. The most important things to check are the pump laser diode's current range and stability along with TEC operation. This driver contains adjustments for modulation and threshold. These adjustments aren't all too important and I won't go into much detail on them. The threshold potentiometer allows for the driver's lowest current to be set. In many DPSS and OPS lasers, this keeps the pump diode just underneath the lasing threshold for better modulation. Fully raising the threshold adjustment allows me to run the laser driver as if I have a safe brightness control on the driver. When I set it to 100%, I can test the full range of the output current. Also notice the addition of an opto-isolator, which serves as an interface between the modulation input section and constant current driver section. I chose to use opto-isolators as they reduce the chances of catastrophic failure from a modulation signal over voltage condition or ESD spike. As I am testing the driver's constant current range, there are also two LEDs I'm watching to make sure that the TEC controllers are operating correctly. One of the LEDs is bicolored and is located in the middle of the driver. When this LED turns red, it's indicating power is going to the TEC with the small heatsink placed on it. The second LED indicator is for the TEC cooling the large LED dummy load. It's tucked underneath the main driver board. This will turn red when power is being supplied to that TEC. On this driver, the laser diode's maximum operating current is once again set by adjusting the potentiometer connected to the TL431. This laser driver functions as expected, though I made this driver with an incomplete knowledge of the laser's exact requirements. Time to get back to learning about the laser so you have a more complete understanding and an easier time than I did. This is the GRIN lens. GRIN is short for Gradient Index. Instead of using geometry to bend light, this optic uses material density. The material in the center is more dense compared to the outside portion of the optic. This makes it a positive meniscus lens without any curve. A glass marble in a clear plastic block would behave in a similar way. The OPS chip is a semiconductor made to convert light. Typically, it plays the role of a multi-level gain medium like neodymium-doped YAG. OPS stands for Optically Pumped Semiconductor. No electricity is required, and this one converts 808 nanometer laser light into 976 nanometer laser light. 976 nanometer laser light from the OPS chip travels through the second harmonic generation optic and birefringent filter. It's then reflected back into the second harmonic generation optic. 488 nanometer laser light produced by second harmonic generation reflects off a dichroic coating on the birefringent filter, and these two optics called for a paradigm shift. This is the birefringent filter, which is typically abbreviated BRF. Inside of the Coherent Sapphire 488-20, it performs two main functions. The first function is as a filter. As a 976 nanometer laser light passes through it, its bandwidth is narrowed significantly. Its second function is to reflect 488 nanometer laser light. This is why one side has a dichroic coating. The BRF is mounted on a small glass pillar. This is to help thermally insulate it. Under the BRF is a PTC heater element. Its resistance is about 100 ohms. Second harmonic generation, typically abbreviated as SHG, is accomplished by the nonlinear crystal lithium triborate, or LBO. In this process, two photons of 976 nanometers combine their energies in the crystal to produce one photon of 488 nanometers. This process I hope to discuss in detail in a future video. Like the BRF, the LBO also sits on a glass pillar, and both of these optics require an exact temperature to operate efficiently. The LBO also contains its own PTC heater. The trick is that there's no external thermistor for sensing. Figuring out how to run these two optics correctly was an interesting endeavor. Back to the drawing board it is, or in this case, perf board. Instead of making the entire driver on a single board, this time I chose to split it back up into discrete sections. Here is the constant current driver for the pump laser diode. I also chose to omit the linearity and threshold circuitry and run the modulation directly into the opto-isolator. As with the laser drivers tested previously, I'll of course test this on a dummy load before connecting it to a laser diode. Modulation is accomplished on this driver by varying the current going from the LM358's output to the base of the transistor by varying the conductivity of the phototransistor inside the opto-isolator. This is determined by how much voltage is going to the LED inside of the opto-isolator. I had tried using an opto-isolator to vary the voltage going to the LM358 from the TL431's connected potentiometer, which is ideally the best place to incorporate modulation. I found the circuit to be more sensitive than I'd liked it to be, so I moved back to the connection between the LM358's output and the transistor's base. There is a chance that the circuit I made can produce current spikes. I have not had any issues though. I thought to be honest and make you aware of this possibility. On the diagram, make note that the opto-isolator can be moved to the connection between the LM358 and the sweeper of the potentiometer. TEC control is still important, and I decided to make an improved TEC driver. For the best results, always remember to use quality components. 1973 was a good year for 555s. Once the driver is connected, the TEC will turn on until the set point of the driver is reached. The driver has 3 adjustment potentiometers, and 2 of them you already know. There are 3 indicator LEDs on this driver, a yellow on the left of the 555 timer for PWM level, a blue one above the 2 potentiometers, and a green above the comparator IC. In this circuit, the PWM and TEC power LEDs are not inverse. The 555 timer's output acts as an enabler, and both will be brighter at higher power. Now, it's tricky to see in this video because of shutter roll affecting how the LEDs actually behave, so please keep that in mind. The green LED indicates the output of the comparator. Both the 555 timer and comparator outputs drive MOSFETs, and both MOSFETs need to be conducting in order for power to be sent to the TEC. You'll notice the blue TEC power LED is only on when the yellow 555 timer LED and comparator LED are on. The comparator has a voltage divider between positive and negative on pin 2, which is made with 2 resistors that are equal. The thermistor and temperature adjustment potentiometer form another divider, which leads to pin 3. Swapping the functions of pin 2 and 3 will invert the functions for heating instead of cooling if needed. This driver is configured to run cool, so if I set the temperature adjustment for a lower temperature, the power and comparator LEDs will remain on until the temperature reaches its cooler set point. It's important to note that the comparator LED continues to cycle and does not remain constantly on. Now I'll discuss a minor issue I had to troubleshoot, and this was how to adjust for changing thermal loads. To demonstrate this, I will connect a large resistor to power, which will generate heat just like the laser pump diode would. Now continue to watch the comparator and power LED, making note of their behavior. You will eventually notice that the green comparator LED locks on and the blue TEC power LED only matches the yellow PWM LED. This happens when the PWM is set too low to accommodate a larger thermal load. Therefore, the TEC remains on due to never reaching the temperature set point. To give me the best of both worlds, the first being able to use PWM to increase temperature stability, and the second to accommodate for changing thermal loads, I made this TEC driver capable of PWM duty cycle modulation. TEC PWM duty cycle can be adjusted through an opto-isolator by applying different voltages to the LED side of that opto-isolator, just as done in the constant current driver. This varies the connection from the sweeper of a second PWM duty cycle adjustment potentiometer to the first. On this TEC driver, the first PWM potentiometer would be set to regulate the pump laser diode's temperature in its threshold range. The upper PWM range for the TEC can be set to match the thermal load of the pump laser diode at full current with the second PWM potentiometer. If dynamic thermal load compensation is not needed, the first potentiometer is set to the point where the TEC can reach the desired temperature range. This is perfect for general cooling, but isn't as stable as it lacks defined power and thermal control, which is best for OPSL and DPSS lasers. If you continue to watch the blue LED, you will see that it starts turning off again for periods of time. This indicates that the TEC is once again regulating at proper temperature. Now to discuss controlling the temperatures of the BRF and SHG optics. For those, I have made another style of driver that is capable of utilizing the PTC heater element in 2 ways. This was accomplished with 2 MOSFETs that switch functions rapidly and a third that can latch on for a brief time using a capacitor. For this demonstration, I will use 2 light bulbs to simulate the PTC heater. Light bulbs are also PTC and their filaments become less conductive when they heat up. They also make a great visual representation of thermal oscillations, and I can discuss that in more detail. Temperature is adjusted using a very similar circuit as the TEC drivers. I'll turn the temperature up and the light bulbs will begin to flash. This flashing is due to an overshoot caused by a larger amount of power than needed going to the light bulbs and a lack of sensitivity on the comparator to compensate. This causes thermal oscillations, and the TECs do the same thing at a much slower rate without controlling their power. These drivers also have a PWM duty cycle that can be set to regulate the power going to the PTC heater, which does a similar task on the TEC drivers. 5 LEDs also indicate function. The green for power in, 3 yellow LEDs, one for PWM duty cycle, a second for MOSFET function, and a third for showing comparator status. Last, there is a red LED, which is parallel to the output of the driver. Calibrating the driver is a bit of a dancing affair, which is typical of lasers and analog hardware. Using both potentiometers, I can get pretty stable operation with minute thermal oscillations. Both the PWM and comparator LEDs must be flashing to show that temperature regulation is active and is not simply PWM duty cycle alone. Make note once again, this activity is not accurately represented due to camera shutter roll. Setting the PTC heater to a higher temperature requires not only the temperature adjustment potentiometer to be set to a higher point, but also the PWM so that the thermal load can be met with little thermal oscillation. This means the PWM will be adjusted so that there is a short sense cycle versus a longer power duty cycle. Now I will set the PTC heater driver to a much lower temperature. To do this, I will first set the temperature adjustment potentiometer lower. Notice that as I set the temperature set point lower, the light bulbs will start to blink more due to thermal load oscillation. To stabilize the temperature at a low setting, the PWM potentiometer is set to a high sense cycle and a low power duty cycle. Both functions are linked, and the PWM duty cycle potentiometer adjusts the duty cycle percentage shared between the sense and power MOSFETs of the driver. It's actually surprising how stable these can get for such a simple circuit. Thankfully, I managed to find light bulbs capable of showing you how these drivers work, as I had not expected the shutter roll on the camera to make reading the LEDs accurately so difficult. I suppose this is a bad time to mention that I left all the LEDs out of the circuit diagrams. All the information you need to make your own driver is in this video, but some of it I'm going to make you work for. On the rear of the ceramic optical deck are bond wires for electrical connections. I'll discuss more on the pinout of these electrical connections later on in the video. The laser light reflected from the mirror discussed earlier travels through the optical pickoff, which reflects a small portion of light onto a photosensor while the majority of light passes through. The beam then goes through a few beam-forming lenses and collimating lens. This is how the laser's optical train works. With that said, there are a few more things to note electrically to make sure your driver has the correct connections. Now for those of you who know what's inside of a sapphire, you'll notice something is missing, and it's not hot glue. For those of you who don't know what's in a coherent sapphire, you'll notice that I made an adapter that goes from the connector on the laser's base plate to the DB25. It's not important how you wire this, as long as the electrical connections correspond properly. Normally inside of a coherent sapphire, there are a few circuit boards. These I want to discuss in a follow-up video I plan to make on a larger version of the Coherent Sapphire 488 lasers. The architecture of the electronics is nearly identical in both, and I think they are hardware hackable, though even if they aren't, it's not going to slow me down that much. I have some other thoughts for the 200 milliwatt Sapphire, such as a glass viewing window. However, it needs some optical alignments, which require micromanipulator tools to do the task, as my sausage fingers aren't good enough. How the Coherent Sapphire 488 lasers compare against DPSS, diode, and argon ion lasers will also be done in detail when the larger version is fixed. This being if everything goes as planned. For a rough comparison, I did put the Coherent Sapphire 488-20 next to my 50 milliwatt Melis Griot. They are both spectacular lasers and have excellent beam quality. Visually, they are nearly identical, though there is a slight difference on camera. Making a driver from scratch has taught me a lot about the OPS lasers and how they work. In doing so, I have gained an appreciation for the minds of the engineers who created these laser systems and the difficulties they went through to get such stable operation. Thank you for watching and allowing me to share what I have learned with you. I hope it helps you get an OPSL running for yourself. And as always, stay tuned for more.